Comet tails are supposed to obey the sun, a universal law every astronomer learns on day one. But when 3I/Atlas rocketed into the solar system in July 2025, its tail bent toward the sun, violating the rule that every comet should follow. Even seasoned experts are now forced to admit Atlas's tail is moving against the solar wind, something never confirmed in the history of space science. If the sun isn't calling the shots, what force is driving Atlas? And why? The answer could change everything we think we know about how the universe works. Every comet that enters the inner solar system faces the same relentless forces. As sunlight warms the icy surface, frozen gases vaporize, dragging dust and debris out into space. This process creates two distinct tails, each shaped by a different driver. The first, known as the ion tail, forms when ultraviolet light from the sun strips electrons from gas molecules around the nucleus. These charged particles, or ions, are swept away by the solar wind, a stream of charged particles racing outward from the sun at hundreds of kilometers per second. Ion tails are unmistakable, thin, blue, and arrow-straight, always pointing directly away from the sun, regardless of the comet's motion or orientation. The second type, the dust tail, is heavier and more diffuse. It consists of larger particles, micron to millimeter-sized grains, released as the comet's ices evaporate. Sunlight itself pushes on these grains through radiation pressure, but the effect is weaker than on the lighter ions. The dust tail curves gently along the comet's orbital path, trailing behind like a streamer caught in a breeze. Even so, the direction is never random. Radiation and gravity combine to ensure that dust tails always bend away from the sun, forming a broad, pale arc that can stretch millions of kilometers across space. For astronomers, these rules are foundational. The sun controls every aspect of a comet's visible structure. The ion tail responds instantly to changes in the solar wind, sometimes flickering or snapping like a blue flame if a coronal mass ejection sweeps past. The dust tail, slower to react, marks the path the comet has traveled, curving gently as the grains lag behind. Both tails are passive, shaped entirely by external forces. The comet itself is simply a source of material. It does not steer or direct its own tail. Textbooks and introductory astronomy courses stress this point. No matter how wild a comet's orbit, the sun always wins. The ion tail points straight out, the dust tail curves away, and the nucleus is left behind, trailing its luminous banners. This is so universal that even the youngest astronomy students learn to predict tail direction by drawing a line from the comet to the sun and imagining the tails pushed outward along that axis. Every major comet in recorded history, from Halley to Hale-Bopp to 2I/Borisov, has obeyed these principles. Images from spacecraft and ground-based telescopes alike confirm the same pattern year after year. The sun's influence is absolute. When a comet's tail breaks this rule, the question isn't just about one object, it's about the basic physics that govern our solar system. July 2025 brings a data stream that few astronomers expected to defend. Atlas, the third interstellar object on record, is now under the gaze of the world's most advanced telescopes. Hubble's WFC-3 captures a fan-shaped plume extending toward the sun, its brightness holding steady for days. The Very Large Telescope, operating in Chile's clear winter skies, confirms the same structure, broad, persistent, and unmistakably sunward. On July 20th, Gemini South delivers a high-resolution sequence. The nucleus flares, dust jets erupt, and the apparent plume stretches nearly 20,000 kilometers in the direction of solar glare. By late July, the Hubble archive logs a series of images that, when stacked, reveal the plume's steady orientation, sometimes even growing sharper as the comet rotates into full illumination. Across continents, observatories scramble to compare notes. The anti-solar tail is present, faint but visible, yet it's the sunward feature that dominates every frame. On August the 3rd, Gemini South's annotated images trace the plume's edge, measuring an extension rate of nearly 150 kilometers per hour. Atlas's survey cameras, running wide-field exposures, corroborate the anomaly from a different angle. The phenomenon persists for over a month. far longer than any solar storm or magnetic event could explain. Every major data archive, ESO, Gemini, NASA's MAST, now contains processed frames and motion vectors pointing to the same conclusion. The sunward plume is not an artifact of a single instrument or a trick of perspective. Hubble's 0.04 arcsecond resolution leaves little room for doubt. Even amateur astronomers, stacking hundreds of images from backyard telescopes, report the same geometry. The consensus among professionals is uncharacteristically blunt. The standard rules aren't holding. Bryce Bolin, one of the first to flag the anomaly, puts it plainly. Instead, its tail is going in the direction of the sun. For a discipline built on centuries of solar dominance, this admission lands hard. The International Astronomical Union convenes an emergency teleconference in late July, drawing in teams from NASA, ESA, and leading comet researchers. Disagreements flare over terminology: plume, anti-tail, jet, but the images are not in dispute. The anomaly is real, cross-checked, and global. No known comet in the modern era has held a sunward dust feature this long across so many independent datasets. The anti-tail grows more prominent in late August, but the sunward plume refuses to fade. As the data mount, textbook certainty gives way to a rare scientific discomfort. The evidence is clear. Atlas is breaking the rule. The sun is not the only force shaping this comet's visible structure. Whatever is driving the plume, it's strong enough to rewrite the boundaries of comet science, at least for now. Solar storms top the list of early suspects. Coronal mass ejections, violent bursts of plasma from the sun, have twisted comet tails before, their magnetic fields yanking charged gas sideways for a few brief hours. But the sunward plume on 3I/Atlas lingers for days, sometimes over a month, outlasting the lifespan of any known solar disturbance. Hubble's July 20th imaging sequence, stitched across a week, captures the plume's unwavering stance against the solar glare. Gemini South's annotated frames, dated August 3rd, clock the same feature holding steady while the anti-solar tail expands in the opposite direction. No coronal mass ejection on record matches that persistence. Attention shifts to chemistry. Some suggest exotic molecules, carbon chains or metallic grains, might alter how sunlight scatters off the dust, tricking the eye and camera alike. But laboratory spectra and VLT's high-resolution photometry tell a different story. Shifts in color or brightness, yes. Directionality, no. The composition of the dust and gas can change how the coma glows, but it cannot force a tail to bend sunward against the solar wind's push. Optical illusions fall next. In the past, odd tail angles have been blamed on perspective, Earth's vantage point lining up stray dust streams to mimic a reversal. This time, the geometry is not so forgiving. Observatories on 3 continents, plus Hubble's orbital perch, all report the same orientation from different angles. Amateur astronomers, stacking images from backyard telescopes, see the same sunward plume. ESA's August summary states it plainly. Current observations align with vigorous outgassing from the sunlit surface, not evidence of unnatural forces. Karen Meach, a veteran of comet outburst studies, weighs in during the IAU teleconference. She points to hyperactive comets in the past, ones that have thrown dust sunward under extreme heating. But even she concedes the scale and duration on display here are without precedent. The standard models, solar wind, chemistry, optical trick, fail to reproduce the data. The anomaly stands, not for lack of effort, but because each explanation breaks down under the weight of multi-instrument evidence and relentless observation. The scientific process clears the board, leaving the next question wide open. August brings a new layer of mystery. Amateur astronomers, armed with backyard telescopes and high-cadence cameras, begin sharing time-lapse sequences of Atlas's tail. In these stitched-together frames, a subtle wave rolls backward along the dust plume, sometimes brightening, sometimes fading, but always moving against the expected flow. What stands out is the interval. Several independent logs from Chile to Japan record the same pattern. A pulse or ripple passes down the tail every 47 minutes, almost on the dot. The effect persists through multiple observing nights, weather permitting, and is flagged on community forums where charts and GIFs spread rapidly. Professional teams at Gemini South and the Very Large Telescope take notice. Their own high-cadence imaging, stacked and annotated, confirms the periodic surges. In one Gemini dataset from August 27th, a brightness wave can be traced moving sunward along the tail, covering nearly 20,000 kilometers in less than an hour. The cadence is too regular for random outgassing or sporadic jets. Even accounting for nucleus rotation or solar wind fluctuations, the timing holds, 47 minutes plus or minus a few seconds. Amateur photometry, normally dismissed as too noisy for fine structure, suddenly becomes a valuable cross-check. The pattern holds across instruments and continents. Michio Kaku, reviewing the compiled data for a late summer panel, voices what many are thinking. Comets are messy, he says, but nature rarely runs on a stopwatch. Regular pulses like these, if confirmed, hint at something more systematic. He points to the difference between chaotic cometary outbursts and the metronome precision now logged in the Atlas tail. We're used to comets that sputter and flare, but this is more like an engine's exhaust. The comparison is hard to ignore. Each pulse coincides with a slight uptick in overall brightness, as if a burst of material is being ejected from the nucleus. The tail's leading edge sharpens, then relaxes, the cycle repeating with machine-like consistency. The cadence is not a known signature from nucleus rotation. Typical comet spin rates range from hours to days, not under an hour. Nor do solar wind variations align with the observed intervals. The regularity, the global conformation, and the direction of the pulses all defy the usual explanations. For the first time, speculation begins to drift from chaotic natural processes towards something more deliberate. The rhythm of the tail pulses, clocked at 47 minutes, challenges the boundaries between cometary physics and controlled emission. As the debate intensifies, the question grows sharper. Is Atlas showing us a new side of interstellar comet behavior? Or is this the first sign of something engineered, hiding in plain sight? Ion propulsion, a mainstay of modern spacecraft, operates on a simple principle: accelerate charged particles, usually xenon ions, using electric fields, then eject them at high speed to generate thrust. The result is a faint, blue-tinted exhaust, nearly invisible in the vacuum of space but unmistakable in long-exposure images. NASA's Dawn mission, for example, used 3 ion engines to spiral through the asteroid belt, each burn producing a whisper of force but achieving major course changes over months. The exhaust plumes, captured in footage from ground and orbit, stretch like narrow, glowing ribbons, visually similar to a comet's ion tail, but with a key difference: every pulse is deliberate, each vector chosen by engineers. Hall effect thrusters, another variant, rely on magnetic fields to direct the ion flow, producing the same signature blue glow and steady, controlled acceleration. In both cases, the exhaust is not a passive byproduct, but the driving force itself, an engine in action, sculpting trajectory with every burst. For Atlas, the analogy is hard to ignore. Where natural comets yield to the sun's pressure, an ion engine pushes back, bending its own exhaust into the void. Atlas's trajectory is now locked on a course that will bring it within 0.19 astronomical units of Mars, just 28 million kilometers, on October 3rd, 2025. For planetary defense teams, this is close enough to trigger urgent debate. NASA's Planetary Defense Coordination Office has reportedly convened closed-door meetings weighing the implications of an interstellar object intersecting Mars's orbital corridor at this distance. The concern isn't just about a flyby. If Atlas's activity intensifies as it nears perihelion, even a modest increase in dust or plasma output could interact with Mars's thin atmosphere. Some officials warn that a surge of charged particles or large dust grains could destabilize the Martian magnetosphere or seed the planet with enough debris to trigger global dust storms. For a world already known for its atmospheric fragility, the risk calculations are anything but routine. The debate spills into discussions of artificial structure. If the nucleus is hollow, or if the tail is being shaped by more than natural forces, Mars could face a threat unlike any in its recorded history. Avi Loeb, chair of Harvard's astronomy department, has never shied away from the extraordinary. In a recent interview, he points to a pattern few are willing to name aloud. Oumuamua, the first interstellar visitor, accelerated without a visible tail. Some called it a light sail, others a cosmic fluke. 2 years later, Borisov arrived, hyperactive but unmistakably natural, its tail trailing in classic fashion. Now, with Atlas, the script grows stranger. The nucleus is brighter, the structure more complex, and the tail refuses to obey the solar wind. Loeb suggests a hollow shell, a casing that could conceal reactors or even mechanisms for propulsion. He notes the rhythmic pulses and the persistent sunward plume as possible signatures of internal activity, not random outgassing. Critics push back, warning against leaping to conclusions, but the escalation is hard to ignore. Each interstellar object has revealed new anomalies, each one closer to the threshold of artificiality. If Atlas is more than a comet, the implications stretch far beyond a single encounter. For now, astronomers are left with a question that resists easy answers. Are we witnessing the handiwork of nature, or the trailblazing signature of something built to travel the stars? On July 1st, 2025, astronomers detected 3I/Atlas, the third confirmed interstellar object to enter our solar system. Over the following months, telescopes around the world documented a tail that, at times, bent toward the Sun, contradicting the established rule that comet tails always point away due to solar wind. Multiple observatories, including Hubble and the VLT, confirmed these anomalies, ruling out instrument error. Standard explanations, solar storms, unusual chemistry, or optical illusions, fail to account for the persistent rhythmic pulses observed in the tail, some recurring every 47 minutes. Despite these findings, there is no peer-reviewed evidence yet of artificial propulsion or non-gravitational acceleration. As 3I/Atlas approaches its closest pass to Mars on October 3rd, 2025, at 0.19 astronomical units, astronomers continue to monitor this unprecedented behavior. The cause of Atlas's sunward tail remains unknown. For now, the evidence forces the scientific community to reconsider what is possible when interstellar visitors defy every textbook rule.